Welcome back. In this brief lecture, we will look back at the strength and shortcomings of the two models that we have discussed over the course of last few lectures. What is the main strength of liquid drop model? It gives us an idea of what nuclear matter is, right? So we started with an notion wherein there is something like nuclear density and it is more or less constant across a range of nuclei. And because of this, there is the binding energy per nucleon is also a constant. These are the main foundations with which the liquid drop model was built. And the consequence of liquid drop model is also important, right? So it gave us the binding energy for a variety of nucleus with and with this you can also get the mass of the corresponding nucleus. So all this suggests that this notion that there is a nuclear condensed matter is a valid notion. Okay, so that gives us a way to visualize the nucleus and gives us a powerful analytical formula for getting to the binding energy as well as the mass of different nucleus. With such a formula, we were able to rationalize the alpha and beta decay as well as spontaneous fission. We have seen all these things in the previous lectures. But what it couldn't do was that this experimental observation of magic clusters, why are some nucleus much more stable than the nucleus in the vicinity of, let's say, similar A and Z, that was not rationalized by the liquid drop model. Despite liquid drop model being able to tell many things, rationalize many things, it was not able to give a clue on magic numbers. It was also not able to rationalize single particle effects like spin, magnetic moments, and parity, because liquid drop model at the end of the day is a collective model. Okay, so it doesn't tell you anything about these single particle models. Moving on to nuclear shell models, the main crux is that it's able to rationalize these special nucleus, okay, which are more stable. Okay, these are the nucleus which have magic numbers. That is rationalized by nuclear shell model, which gave it a lot of credibility. It is built on single particle effects, wherein each particle moves under an effective potential provided by the rest of the um, uh, particles. So this is very, very different from that of the liquid drop model. If the liquid drop model suggests nuclear matter is like condensed matter, the nuclear shell model seems to suggest it is like a dilute gas, right? Wherein each particle is able to move in some effective um, potential. Um, and nuclear shell model was able to rationalize a variety of things, right? It was able to give the why magic numbers exist. It gave some idea of nuclear isomerism and so on. If you, when you try to improve the nuclear shell model, okay, like what you see in electronic structure. Electronic structure, the general features were obtained from a shell model, but when you want to quantify that, it becomes very, very computationally intensive. You might have heard in electronic structure something called Hartree-Fock approximation, okay, density functional approximation. Similar models do exist for nuclear shell structure also. You have Hartree-Fock approximation. In the last couple of decades, density functional approximations have also been utilized. Okay, so but however, making it more quantitative is not that easy. It becomes computationally intensive. But if you want to get an idea of uh, what is nuclear structure, a good understanding of both the drop model and nuclear shell model is important. So you should spend some time thinking through both these models and understanding it in some detail uh, within the scope of this course. Thank you.